All right, so the remaining part of chapter 2, the last section of it, deals with one of the properties of matter known as density. And density is a property of matter that's known as an intensive, or sometimes it's called intrinsic property, or characteristic is another name for that, of matter. And what does that actually mean? Well, this means that density does not depend on how much of the sample you have. So it does not depend on how much of the sample you have. So for example, if you have 1 gram of gold, it would have a certain density. If you have a kilogram of gold, it would have the exact same density. And that is because density is a ratio of a substance's mass to its volume. So we can write that equation, or the relationship between those two properties, as density is equal to mass over volume, or more simply, D is equal to M over V. Right? So it's a ratio of the mass of a substance to the volume that it occupies. And as you probably know, different substances have different densities associated with them. So in this diagram here, you're seeing what can actually happen when you place substances that have different densities next to each other or in a common environment. So for reference here, we have the density of water as 1.00 grams per mil. And then you'll notice the substances that have a greater density than water, such as the aluminum and the lead, they actually sink to the bottom of the container, whereas the substances that have a lower density, such as the cork and the ice, they tend to float in water, right? So we can come up with a general statement about that. So we can say compared to water, substances with a greater density tend to sink, whereas substances with a lower density tend to float, right? And we can make some pretty solid conclusions just based on what we observe when we place something in water. So we mentioned that density is equal to mass over volume. And as such, the units of density will reflect those units. So typically, the unit of mass that we'll use is grams per milliliter for liquids, or just simply grams per mil, or G over ml. And then for solids, we typically see grams per cubic centimeter, or G over cm cubed. Right, remember, we talked about this last time. 1 mil is the same as 1 cubic centimeter. Right, so what this means is something that has a density of 15 grams per milliliter is the same as 15 grams per cubic centimeter. right? Because of that one-to-one relationship between the mil, or the milliliter, and the cubic centimeter. So those are going to be the most common units that we see for density. It's not that there aren't other units, because there are, especially when it comes to things like gases, for instance, over here, whose densities are in grams per liter, right? And that's because of the nature of gases. They tend to occupy a much bigger volume compared to liquids and compared to solids. So, you probably have heard the term density before, maybe in some detail, maybe not as much detail. Where this is linked to health. One instance where it's linked to health is in the condition known as osteoporosis, where there's the thinning of the bone, where the bone actually is less dense than it's supposed to be, and that's due to the loss of bone minerals, which ends up being a result of maybe diet or just environment. So on the left side here you see normal bone, on the right side you see a bone with osteoporosis, and you can see there's just less material in here. There's less mass in there, even though it occupies the same volume, which would make the density lower. And then as a result, less dense bone tends to be a little more fragile than bone that is denser. And then, in the lab or at the doctor's office, X-rays are typically used to take a look at bone. So when it comes to measuring density in the lab, some of you had lab this week, some of you didn't because of the snow day. But there's a very common technique called displacement, where we can actually measure the volume of a substance, and that together with the mass we can use to measure the density. So for instance, this is something that you did in the lab, and if you didn't, I'm going to walk you through what this is, because you're going to collect some data. I'm going to give you some data for the lab, and you'll actually be able to do the lab on your own, those of you that didn't have lab this week. So we have here on the left side a metal cylinder, and we can actually measure the mass of that metal cylinder using a balance. Now, because of the shape of the cylinder, it may be difficult to measure the dimensions and calculate the volume. So instead, what we use is a technique known as displacement to measure the volume. And the principle behind this is relatively simple. This says that a substance will displace a volume equal to its own volume. And you can think of an example of this. If you fill your bathtub at home with water and you get in to the bathtub, the level of the water goes up. Well, you displace a volume equal to your own volume. And it's the same idea here. So on the left side here, we have a graduated cylinder. We fill it up to this volume. So that's our initial volume that we have. And then we take our metal cylinder and then we add it into the graduated cylinder. And as a result, the level of the liquid goes up, and we can measure what that final volume is. So then the volume of the metal cylinder, we can calculate that by doing a simple subtraction, and that is equal to the final volume minus the initial volume. All right, and then we can plug that into our density equation. So we can say the density of our zinc cylinder there now is the mass of the zinc, which we measure at 68.60, divided by the volume, which is now simply the difference. All right, so this here is our final volume minus the initial volume, which gives us 9.5. And then we end up with 7.2 grams per mil. Along the way, as you probably realize, we're keeping track of sig figs. All right, so that's a relatively simple way to measure the volume by displacement. That together with measuring the mass using a balance, we can divide the mass by the volume to end up with the density, and that's what you did in the lab. And those of you that didn't have lab, that is what you would have done in the laboratory. So those of you that did not have lab, I will upload a document that's going to have some sample data for you to use to do your calculations. It'll contain the mass of the different samples together with these values here, the initial and the final, and then you can calculate what the volume of the cylinders happen to be. All right, so if we take a look at an example over here, we have we need to calculate the density in grams per mil of a 48.0 gram sample of metal, right? So right away we know that this is the mass. If the level of the water in the graduated cylinder rises from 25 to 33 after the metal is added, right? So this 25 is what we start with. That's our initial volume. We add the metal in here and the volume goes up to 33. This will be our final. So then the volume of the metal cylinder is the final volume minus the initial volume, which is 33.0 minus 25.0 mils. All right, and that'll be 8.0 milliliters. So that's our volume of the cylinder. We have our mass up here is 48.0, so then we can calculate the density as being 48.0 grams divided by 8.0 mils, and then we get our density, whatever that happens to be. I'm not going to go through that. I think that's something that you can plug into your calculator relatively simply. So when it comes to density, we saw how we can calculate it or determine density in the lab. We can also use density as a conversion factor if we needed to. All right. So for instance, if we say that the density of aluminum is equal to 2.70 grams per cubic centimeter, right? This here is something that we can use as a conversion factor, right? So this is telling us that 2.70 grams of aluminum, or aluminium if you want to pronounce it that way, is the mass of 1 cubic centimeter. That is a conversion factor by definition, and as such we can use it also by just simply inverting it. So a volume of 1 cubic centimeter would have a mass of 2.70 grams of aluminum, right? So we can treat this the exact same way like we would any other conversion factor by using the tools that we learned previously. So let's see how we can incorporate this into an equation or a problem. So we have here our problem given. So we said an unknown liquid has a density of 1.32 grams per mil. What is the volume of a 14.7 gram sample of the liquid? So what are we given? We're given the density 1.32 gram per milliliter. We are given the mass of the sample as 14.7 grams, and what we need is the volume, right, in milliliters. So we can start what's given, or before we set it up, what are we going to use, right? What actually relates what we need to what we're given? And that is density relates mils to grams. So we start with what's provided. We have our 14.7 grams that we have. And now we can take our density over here and we can insert this as a conversion factor, again, using our units as a guide, right? So this here is the same thing as saying 1.32 grams per mil, or we can flip it and we can say 1 mil for every 1.32 grams, right? So that's the same exact thing we did with all the other conversion factors, whether it was metric or otherwise. So now our units are going to guide us, and it's going to tell us we're going to use this one as our conversion factor that we're going to add in here or put in here so that the grams underneath can cancel out. And we end up with milliliters as our unit. And that's going to give us 11.1 milliliters as our volume. All right, remember now we're going to keep track of our sig figs. This here has 3 sig figs. Our density has 3 sig figs. We're just multiplying and dividing, so our final answer is going to have 3 sig figs as well. All right, so we can use density as a conversion factor. All right, let's take another quick look at an example. It says John took 2 teaspoons of cough syrup for a cough. The cough syrup had a density of 1.20 grams per mil, and there is 5 milliliters in 1 teaspoon. What is the mass in grams of the cough syrup that he took? All right, so again, let's organize. What are we given? We're given the fact that he took 2.0 teaspoons. We're given the fact that the density of the syrup is 1.20 grams per mil. And we're given the fact that there is 5.0 mils in 1 teaspoon. All right, and what we need is the mass in grams. All right, so we mentioned before that the density itself can be used as a conversion factor. Now we're given this relationship, which is an equality. And as we said before, we can make that into a conversion factor as well. So 1 conversion factor, or we can flip it, 1 teaspoon as 5.0 milliliters. So when we set up our problem, all right, we're going to start with what's given, which was the fact that he took 2 teaspoons of cough syrup. Then I can take one of these 2 conversion factors here. If I want teaspoon to cancel, I'm going to take that one that has teaspoons on the bottom. And now I can use my density as a conversion factor. Again, my units being my guide. If I want mils to cancel, 1 mil goes on the bottom. I have 1.20 grams on top. So mils can cancel. I have grams as my unit, which is what I needed. And I can go ahead and multiply out my numbers, right? So I have 2 sig figs over here. I have 2 sig figs on this side. And I have 3 sig figs here. So my final answer then, whatever that is, has to have 2 significant figures. All right, so here we're incorporating a couple conversions right after each other. We have density, and we also have the relationship between teaspoon and milliliters. So one place, especially in the health field, where you would encounter a derivation of density is when you look at the specific gravity of something. And the specific gravity is defined as what's calculated as dividing the density of a particular sample by the density of water. And the density of water is just 1 gram per mil. So when you divide the density of something by the density of water, really you end up with the same number, right? Because you're just dividing it by 1. This here, the density of water is 1 gram per mil. And the density of the sample can be whatever. Let's say it's 5 grams per mil. Well, then your units are going to cancel out, and you just end up with 5. Right, so the specific gravity doesn't have any units because you're comparing it to the density of water, so the units cancel out, and it's the same value, except now without units. So it's a relationship or a comparison to water. The device used to measure specific gravity is called a hydrometer, and it's used quite frequently to measure the specific gravity of urine. which has a particular range associated with it. And the reason why that's important is because we can use that to gauge whether somebody has some sort of kidney disease or type 2 diabetes. Right? So the specific gravity of one's urine can actually be an indication of that condition, or maybe there's dehydration, or in some cases, liver disease. In a typical, clinic or hospital, for instance, there's a quick way to measure it. There are these color-coded sticks that can be used. They change color based on the specific gravity of the substance that they are testing.